Next, we turn to refrigerant and steam.
I would like to introduce the properties table for saturated liquid and saturated vapor of refrigerant 717, which is ammonia. This table lists temperature in the first column, pressure in both Sia and Sig, and also provides the specific volume of vapor Vg, the reciprocal of liquid density 1/Vf, and the vapor-specific gravity Sg. The temperature range is listed in 1-degree increments from -105 degrees Fahrenheit to -60 degrees Fahrenheit. For example, at -105 degrees Fahrenheit, the pressure is 0.996 Sia. The vapor-specific volume Vg is 223.2, the liquid density is 45.71, and the Sig value is -27.9. When the temperature rises to -60 degrees Fahrenheit, the pressure becomes 5.55 Sia, the vapor-specific volume is 44.73, and the liquid density is 43.91. The parentheses attached to the Sig value are a note indicating that the value is expressed in inches of mercury for vacuum conditions. You can see from the table that as the pressure increases, the vapor-specific volume Vg decreases significantly from 223.2 to 44.73.
I'd like to introduce the enthalpy and entropy property tables for refrigerant 717, ammonia. Enthalpy is provided in BTU per pound, divided into liquid value HF and vapor value Hg. Entropy is in BTU per pound Rankine, and here we see the liquid value SF. This table is a continuation of the previous one, containing saturated state values from -68.5 degrees Fahrenheit to -21.2 degrees Fahrenheit. For example, at -68.5 degrees Fahrenheit, the liquid enthalpy HF is -68.5, the vapor enthalpy Hg is 570.3, and the liquid entropy SF is 1.6243. As the temperature rises to -21.2 degrees Fahrenheit, the vapor enthalpy increases to 589.6, and the liquid entropy decreases to 1.4769. In other words, as temperature increases, vapor enthalpy tends to increase while liquid entropy tends to decrease.
I'd like to introduce the density column of the fluid property table. The unit for density, indicated as density in the header, is lb/ft superscript 3. This value represents mass per unit volume, and in the saturated state table, the densities of the liquid state and vapor state are listed separately. Since density has an inverse relationship with specific volume, density can be calculated as 1 divided by specific volume. This property is used as a basic input for CV calculations or mass flow rate conversions.
I'd like to introduce the specific volume column. This column, labeled as volume, refers to specific volume, and the unit is FT superscript 3/pound. Specific volume is the volume occupied by a unit mass and is the inverse of density. That is, specific volume is 1 divided by density. In the saturated state table, it is divided into liquid-specific volume VF and vapor-specific volume VG. In particular, the vapor side specific volume varies significantly depending on pressure and temperature.
I'd like to introduce the saturated liquid and vapor property table for ammonia, also known as refrigerant 717. This table uses Fahrenheit temperature as the independent variable, and the excerpted section ranges from -59 degrees Fahrenheit to -14 degrees Fahrenheit. Pressure is presented in 2 columns, gauge pressure in Sig and absolute pressure in Sia. Looking at the pressure values at -28 degrees Fahrenheit, the gauge pressure is 0.0, which corresponds to atmospheric pressure. At temperatures lower than that, values are shown in parentheses which indicate vacuum pressure in inches of mercury in Hg. Other properties listed include the specific gravity of vapor and liquid as Sg and Sf, enthalpy as Hg and Hf, and the inverse of specific volume as 1/Vf and vapor-specific volume Vg. For example, at -28 degrees Fahrenheit, the liquid side specific volume related item is read as approximately 18.00.
I'd like to introduce the enthalpy and entropy columns of the ammonia saturation table. The unit for enthalpy is BTU/lb, and the unit for entropy is BTU/lb degree R, based on the Rankine absolute temperature. Liquid enthalpy HF starts at approximately -20.1 and increases to 27.8 BTU/LB as the temperature rises. On the other hand, vapor enthalpy Hg stays within a relatively narrow range, from approximately 590.0 to 607.1 BTU/pound. At the reference point of the table, both enthalpy and entropy pass through 0.0, which indicates the zero setting at the reference temperature. Liquid entropy SF varies from -0.0490 to 0.062, and vapor entropy Sg decreases from 1.4741 to 1.362 as temperature increases. Footnote 1. In the header indicates that these values were calculated based on a specific reference state.
As the ammonia saturation table we saw previously continues into the next temperature range, I'd like to introduce the density column that appears again. The unit in the header remains LB/FT superscript 3. Because such long property tables are divided by page or temperature range, the column headers are repeated. Density is provided separately for liquid and vapor, and it corresponds to the specific volume column in the same table as an inverse relationship. Generally, as temperature increases, liquid density tends to decrease and vapor density tends to increase.
I'd like to introduce the specific volume column that reappears in the next section of the ammonia saturation table. The unit is FT superscript 3/LB, and it has an inverse relationship with the density in the same section. That is, specific volume is 1 divided by density. Specific volume is also divided into liquid specific volume VF and vapor specific volume VG. Notably, under low temperature and low pressure conditions, the vapor specific volume has a very large value. When using this property table, first find the corresponding row by Fahrenheit temperature and then read the value from the required column among pressure, enthalpy, entropy, density, and specific volume.
I would like to introduce the section of the properties table for refrigerant 717 ammonia that organizes the pressure and temperature ranges. This table consists of temperature in degrees Fahrenheit, gauge pressure in Sig, absolute pressure in SIA, liquid inverse specific volume 1/VF, vapor specific volume VG, enthalpy for liquid HF and vapor HG, and entropy SF and SG. Temperatures are listed in precise 1 degree intervals, starting from around -13 degrees Fahrenheit up to above 0 degrees Fahrenheit, allowing for detailed lookups. Looking at the absolute pressure, it is 21.99 SIA at -13 degrees Fahrenheit, and increases as the temperature rises, reaching approximately 29.69 near -1 degree Fahrenheit, and up to 31.92 in the 5 degrees Fahrenheit row. The gauge pressure starts at 7.3 Sig at -13 degrees Fahrenheit, reaches 16.5 near 0 degrees Fahrenheit, and gradually rises to 47.6 at the end of this section. The 1/VF value, which corresponds to liquid density in LB/FT superscript 3, is 41.91 at -13 degrees Fahrenheit and decreases as temperature increases, reaching 39.86 at the end of this range. The usage is simple. Find the operating temperature in the row, then read the corresponding pressure, density, specific volume, and heat values in the same row for design and selection.
Following the previous pressure and temperature range, I would like to introduce the enthalpy and entropy data for the same temperature range. Liquid enthalpy HF and vapor enthalpy Hg are in BTU per pound, and entropy SF and Sg are in BTU per pound R. Liquid enthalpy increases monotonically from about 28.9 BTU to 77.9 BTU. On the other hand, vapor enthalpy increases relatively gradually from 607.5 BTU to 621.0 BTU. A key point here is that the difference between vapor enthalpy and liquid enthalpy, which is the latent heat of vaporization, gradually decreases as the temperature rises. Regarding entropy, liquid entropy SF increases from 0.0666 to 0.1708 BTU/LBR, while vapor entropy Sg decreases from 1.3624 to 1.2755. Footnote 1 of the table indicates that these enthalpy and entropy values are saturated values based on the reference point defined in the table.
This chunk introduces the part that defines the header for the density column in the refrigerant 717 properties table. The column title is Density, and the unit is pounds per cubic foot, lb/ft superscript 3. This column indicates how much mass the saturated liquid and vapor have per unit volume, and it directly represents liquid density in connection with the 1/VF item we saw earlier. When designing based on volumetric flow rate, this density value is used to convert it into mass flow rate.
This chunk introduces the part that defines the header for the specific volume column in the refrigerant 717 properties table. The column title is volume, meaning specific volume, and the unit is cubic feet per pound, feet superscript 3/lb. This column represents the saturated vapor specific volume VG, which means the volume occupied per unit mass. Since it is the reciprocal of the density, lb/ft superscript 3, we saw previously, you can immediately calculate one value if you know the other.
Following the low temperature section, I would like to introduce the high temperature and high pressure section of the same refrigerant 717 properties table. This part is a continuation of the table, covering higher temperature and pressure regions. Absolute pressure starts at approximately 63.59 psi and rises to 147.9 psi, while gauge pressure increases monotonically from 48.9 to 133.2 sig. Vapor-specific volume VG decreases from 4.547 feet superscript 3/lb to 2.021 ft superscript 3/lb, because as pressure increases, the vapor is compressed and the volume occupied by a unit mass becomes smaller. The 1/VF value, corresponding to liquid density, decreases gradually from 39.82 to 37.58. In summary, as temperature rises, pressure increases, while vapor-specific volume and liquid density both tend to decrease. The usage is the same. Find the temperature for the high-pressure operating condition in the row, and directly look up the pressure, density, and specific volume values in the same row.
Finally, I would like to introduce the enthalpy and entropy data in the high-temperature section of the refrigerant 717 properties table. As before, the units are BTU per pound for enthalpy and BTU per pound Rankine for entropy. Liquid enthalpy, HF, increases from approximately 79.0 BTU to 129.7 BTU, while vapor enthalpy, HG, increases gradually from 621.2 to 630.4 BTU. In this high-temperature range, you can see that the difference between vapor enthalpy and liquid enthalpy, the latent heat of vaporization, becomes even smaller than in the low-temperature section. For entropy, the liquid side, SF, increases from 0.1730 to 0.2706 BTU per pound Rankine, whereas the vapor side, SG, decreases from 1.2738 to 1.2020. As indicated by footnote 1, these are all enthalpy and entropy values based on the saturated state.
I would like to introduce the density entries in the saturated liquid and saturated vapor properties table for refrigerant 717, which is ammonia. The header for this column is density, and the unit is pounds per cubic foot. This table presents the densities of liquid and vapor respectively according to temperature and pressure under saturated conditions. The density column, combined with the subsequent specific volume, enthalpy, and entropy columns, forms one large properties table. Since density values are used directly as fluid input when sizing valves and piping, it is important to accurately recognize that the unit is pounds per cubic foot.
Next, I will introduce the specific volume entries in the ammonia properties table. The unit for the specific volume column is cubic feet per pound, which is the reciprocal of the density we saw earlier. This table provides the volume occupied per unit mass for both saturated liquid and saturated vapor. In particular, the specific volume of vapor is used as a key input when calculating pressure drop and flow velocity. Since density is in pounds per cubic foot and specific volume is in cubic feet per pound, the two values can be converted into one another.
I would like to introduce the body structure of the ammonia saturation properties table. Each row is based on the Fahrenheit temperature, and the corresponding saturation pressure is presented in both sig and psi units. The table is arranged with columns for vapor-specific volume Vg, the reciprocal of liquid density 1/Vf, liquid enthalpy HF and vapor enthalpy Hg, and the specific weights of liquid and vapor, SF and Sg. Liquid enthalpy starts at 150.5 at the top of the table and increases down to 307.8 BTU per pound, while saturated vapor enthalpy ranges from 135.8 to 293.1 BTU per pound. Vapor-specific volume decreases from 1.988 to 0.973 cubic feet per pound, and liquid density decreases from 37.53 to 34.96 pounds per cubic foot. The reference pressure is 14.696 psi, and standard cycle temperatures, such as 86 degrees, are marked separately.
I will now introduce the footnotes and reference conditions for the ammonia saturation table. First, the enthalpy values use a reference point where the saturated liquid at -40 degrees is set to 0. Second, vacuum pressure lower than atmospheric pressure is expressed in inches of mercury below 1 standard atmosphere, which is necessary when interpreting negative gauge pressures in the table. Third, some rows in the table correspond to standard cycle temperatures used in refrigeration cycle analysis. This entire table covers the liquid and saturated vapor properties of refrigerant 717, ammonia, and the title is Properties of Liquid and Saturated Vapor, Continued.
I would like to introduce the body values for enthalpy and entropy in the ammonia properties table. The unit for enthalpy is BTU per pound, and the unit for entropy is BTU per pound Rankine. Liquid enthalpy, HF, gradually increases from 130.8 to 177.8 BTU per pound, and vapor enthalpy, Hg, converges gradually from 630.5 to 634.0 BTU per pound. Meanwhile, liquid entropy, SF, increases from 0.2728 to 0.3535 and vapor entropy, SG, decreases from January 2006 to 1.1510. These entropy values, like the enthalpy values, follow the reference point where the saturated liquid at -40 degrees is set to 0.
Finally, I will introduce the values for the continued section of enthalpy and entropy in the ammonia properties table. This part is the bottom section continuing from the previous table, where vapor entropy, Sg, continues to decrease from 1.1510 to 1.1358 BTU per pound Rankine. Liquid enthalpy, HF, still increases from 179.0 to 185.1 BTU per pound, while vapor enthalpy, Hg, reaches saturation and remains almost constant around 634.0 BTU per pound. Liquid entropy, SF, increases from 0.3576 to 0.3679. You can see the trend of vapor enthalpy flattening out as you move toward the bottom of the table.
I'd like to introduce the data column configuration of the conversion table, summarizing the physical properties of water. This table lists the saturation pressure in psi on the left, along with the corresponding temperature, entropy, enthalpy, and specific gravity. Looking at the low temperature range, the saturation pressure starts at very low values such as 0.0885, 0.117, 0.1781, and 0.2653 psi, and the pressure gradually increases as the temperature rises. The row corresponding to standard atmospheric pressure is 14.696 psi, where the specific gravity is around 0.9594. As pressure increases, it continues to 134.63, 247.31, 422.6, 680.8, 1045.2, and 1542.9 psi, with the final row reaching 3093.7 psi, which is near the critical point. At this point, the specific gravity drops significantly to 0.4347. Please keep in mind that the specific gravity starts at 1.0013, based on 60 degrees Fahrenheit, and decreases monotonically as pressure and temperature increase.
Now, I'll explain how to convert the flow rate of water from pounds per hour to gallons per minute. The core concept is simple. Multiply the flow rate expressed in pounds per hour by the conversion factor listed in the table to obtain the flow rate in gallons per minute. Here, the weight per gallon is calculated based on the standard of 7.48 gallons per cubic foot. The table organizes this conversion factor alongside the specific gravity at 60 degrees Fahrenheit and the weight expressed in pounds per gallon. Therefore, when you have mass flow data in the field, you can immediately convert it to volumetric flow with a single multiplication using the factor from this table.
I'd like to introduce the column headers of a table summarizing the properties of saturated steam. This table uses the temperature value, T, expressed in Fahrenheit, and the pressure in pounds per square inch as the basic variables. In other words, the temperature is on the left, paired with the steam pressure at that same state. In the subsequent tables, the absolute pressure, P backslash, expressed in inches of mercury, the vacuum, and the corresponding temperature are presented, so you can consider this slide as the definition of the reference variables used to read that data.
I'll explain the data correspondence in the saturated steam table. This table shows the absolute pressure P backslash in pounds per square inch, the same pressure in inches of Hg, and the corresponding vacuum Hg and saturation temperature. In the lowest range, when P backslash is 0.20 psi, the absolute pressure is 0.41 inches. Hg, the vacuum is 29.51 inches. Hg, and the saturation temperature is 53.14 degrees Fahrenheit. When P backslash becomes 1 psi, the absolute pressure is 2.04 inches. Hg, the vacuum is 27.88 inches. Hg, and the temperature is 101.74 degrees Fahrenheit, which is close to the boiling condition near atmosphere pressure. In the middle range at P backslash 5.0 psi, it shows an absolute pressure of 10.18 inches. Hg, a vacuum of 19.74 inches. Hg, and a temperature of 162.24 degrees Fahrenheit. Moving toward the upper limit of the table, at P backslash 10.0 psi, the temperature is 193.21 degrees Fahrenheit, and in the final row, at P backslash 14.0 psi, it reaches an absolute pressure of 28.50 inches. Hg, a vacuum of 1.41 inches. Hg, and a saturation temperature of 209.56 degrees Fahrenheit. In summary, you can see a consistent trend where, as the absolute pressure increases, the vacuum Hg value decreases from 29.51 to 1.41, and the saturation temperature rises from 53.14 to 209.56 degrees Fahrenheit.
I'd like to introduce the latent heat item covered in the saturated steam table. Here, latent heat refers to the amount of heat absorbed or released without a change in temperature when a substance changes phase from liquid to vapor. This heat appears as a separate data column header in the saturated steam properties table, and the units are linked to the BTU per pound system, same as in the following tables. Since the latent heat value varies depending on the pressure and temperature conditions, it is an essential item to reference when calculating the heat balance in steam system design.
I'll introduce the heat data group in the saturated steam table. This section covers two core types of heat. First is the latent heat of evaporation, which represents the heat required to convert 1 pound of water into steam at the same temperature, expressed in BTU per pound. Second is the total heat of steam, which is the total heat obtained by adding the latent heat of evaporation to the sensible heat held in the liquid state, also expressed in BTU per pound. These heat values are organized in the table paired with the pressure conditions in inches of Hg, allowing you to immediately read the energy held by saturated steam at a specific pressure and temperature. This data column is the final group organizing heat in the saturated steam properties table.
I'd like to introduce the center column configuration of the saturated steam properties table. This table gathers and organizes the pressure, temperature, energy, and volume-related properties of steam when it is in a saturated state. For the energy items, the heat of the liquid is shown in BTU per pound, and the latent heat of evaporation and total heat are also presented in the same BTU per pound unit. For the volume item, there is the specific volume, which represents the volume occupied per unit mass in cubic feet per pound. This section is the header area that defines which properties should be read in which unit, and the specific numerical values will be covered in the subsequent data rows. When reading the specific volume, remember that the unit is cubic feet per pound.
I'd like to introduce the values for the low temperature range among the data rows of the saturated steam table. First, the enthalpy of liquid starts at 21.21 BTU/LB and steadily increases as the temperature rises, passing through 44.41, 66.21, and 90.14 up to 106.68, 130.13, and finally 161.17 BTU/pound. On the other hand, the latent heat of evaporation gradually decreases from 1063.8 to 979.3 BTU/LB. This is because as pressure and temperature increase, the heat required to convert liquid into steam decreases. The total heat increases gradually from 1085.0 to 1143.3 BTU/pound. An important relationship here is that the total heat is the sum of the enthalpy of liquid and the latent heat of evaporation. For example, adding 1063.8 to 21.21 gives approximately 1085.0. The specific volume decreases very rapidly from 1526.0 to 708.5 and then down to 38, showing that at lower pressures and temperatures, the same mass of steam occupies a much larger volume.
I'd like to explain how the pressure and temperature columns are defined in the saturated steam table. The pressure column is listed in pounds per square inch or psi. The temperature column represents the saturation temperature in Fahrenheit, denoted by the symbol T in degrees Fahrenheit. When using this table in practice, you first determine the operating pressure, and then read the corresponding saturation temperature and various physical properties from the table. Since pressure is provided as both gauge pressure and absolute pressure, you must verify which standard your pressure follows before reading the value from the same row. This section covers the header definitions, and the specific pressure and temperature values will be discussed in the subsequent data rows.
I'd like to introduce the area around atmospheric pressure, which is a core data section of the saturated steam table. The reference point is an absolute pressure of 14.696 psi, which corresponds to a gauge pressure of 0.0 sig, or atmospheric pressure. At this point, the saturation temperature is 212.00 degrees Fahrenheit, the boiling point of water. The difference between absolute pressure and gauge pressure is always constant at 14.696 psi. For example, an absolute pressure of 20.0 is a gauge pressure of 5.3, and an absolute pressure of 30.0 is a gauge pressure of 15.3. This table covers the range from absolute pressure 14.696 through 20.0, 25.0, 30.0, 40.0, and 50.0, up to 54.0 psi. The corresponding saturation temperatures rise from 212.00 to 227.96, 240.07, 250.33, 267.25, 281.01, and finally up to 285.90 degrees Fahrenheit. In other words, it shows a monotonically increasing relationship where the temperature at which evaporation occurs rises as pressure increases. These pressure and temperature values pair with the specific volume column in the same table to complete the physical properties of saturated steam.
I'd like to explain how the heat-related columns are defined in the saturated steam table. First, the latent heat of evaporation refers to the heat required to convert liquid into steam at the same temperature, expressed in BTU per pound. The enthalpy of liquid refers to the sensible heat used to heat water from a reference temperature to the saturated liquid state, also in BTU per pound. Then, the total heat is defined as the sum of these two, the enthalpy of liquid and the latent heat of evaporation. Generally, as pressure and temperature increase, the latent heat of evaporation tends to decrease. This section defines the headers of the heat columns, and the actual values will be covered in the following data rows. When reading the table, you can easily verify the consistency of the values by remembering that the total heat is the sum of the two columns.